Okay, good morning. So today we have the second presentation of this new series of Friday at ISISE. Thank you for your participation, but also thank you, Luís, for the presentation. This second presentation will be made by Luís Silva, and it is named Performance of the Modular Hybrid Cold-Formed Steel Tubular Structural System, which will make a presentation of around 20 minutes. After we have a discussion with a colleague, Mariela, for 10 minutes. And after that, we have the public discussion with all of you, the ones that have some questions. So we intend to finish before 1 o'clock. Okay?
Okay.
Good.
Thank you. Thank you for the intro. Welcome you all for coming. Thank you all for coming as well. My presentation, as Professor Aldina said, is called Performance of a Modular Hybrid Cold-Formed Steel Tubular System. However, this title is very specific to the system, and my project, my work, is more specifically to do with the connection itself. So have that in mind. Don't be tricked by the title itself right here. So I'll briefly go through it. So I'll start with a brief introduction, some contextualization of the connection that I'm going to present to you. The description of the hybrid innovative system, what we have done in terms of experimental tests, the replication in numerical modeling as well, some characterization of components, of what we deem more or the most important components of this connection, and some brief conclusions as well, because this is a summarized presentation, otherwise we'll be here a long time. So this project is born from this work is born from the project called Inno3D Joints, where the idea was to create a connection where it would be very simple to apply on site, and it's basically summarized by a socket or a pair of sockets, a pair of plugs, what we call plugs. However, the green part, the plug, could be separated into two, where there's some kind of a T-stub on the left and what we call a fork on the right. So also have those terms in mind. So the idea was to create the whole connection, where the idea was to connect two types of structural elements, in this case light steel framing girders and hollow section columns. As we can see some little GIF here, and how the building is conceptualized. We can also see a real life example at the laboratory here at ISISE, so if you're interested. So the idea is also to develop the design guide and everything else, so this could be applied into practice. So also the work plan, as you all figured by now by the introduction, should start with the literature review. We should talk about connections and hybrid solutions that exist already, some hybrid solutions, because these also could include the behavior of the slab itself in cross-laminated timber. So if this is also accounted for, we can call it a hybrid system. So we have the experimental tests. Here are some photos as well. The replication in terms of numerical modeling, some technological aspects, because this in real applications is unavoidable in terms of gaps, and, the usual things. Then we have the characterization of components, where we identify and characterize each new component. In this case, the two parts, the components that are included in the two parts that I presented in the last slide, the socket and the plug. And finally, the design and final writing and dissemination of this work that is being done. So, I'm sure that you already understand how the connection works, but just in case, this is supposed to be an easy to assemble joint, where the plug is already welded, comes already welded from the workshop to the site. The same happens with the truss girder, already has bolted in the plug part, and this is supposed to work as an actual spring in up and in down. So here, in this case, they are represented as rigid links, but they are not. They are an assemble with some length, which is also another problem that we have in terms of the developing of this joint, which has a length around to 20 to 35 centimeters. Designed for modular construction, as you can imagine. To mount a structure like this would be relatively easy as long as everything comes out correct from the workshop. The idea is to have two actual forces acting in opposite directions. We have then a moment resisting joint, and after all the work is done, after all is processed, we have a design guide according to current rules. These are the general dimensions of the joint, but we'll see that they are actually used. Also, that we should notice that a socket can or may not have the stiffness to make the joint stronger. This is a simplified model of the spring chain. In this case, we should probably see that this part is neglected, although this is not totally neglected, because the idea so far is to include it in the stiffness of the socket somehow. So we don't have an extra component, but we have a component that includes the T-plug. I usually call this the T-plug, although it's pretty much a T-stub. Since there are no bolts, we'll call it a T-plug. So for this work, this is also a very summarized slide where some initial tests have been done, where we tested different types of truss girder and columns, in this case hollow section columns, cold formed. We also, so this is pretty much the summary of both results. We also tested the system if the OSB is used. Of course, as you can see in the bars, the lateral stiffness of the two OSB goes like 2 to 3 times the lateral stiffness of the system of the frames without the OSB, which is understandable. From this test, we decided on the shape of the column, which should be squared to be more applicable to 3D environment. So if it's rectangular, it's more complex. And we decided also on the shape of the light steel framing. So, to start the experimental test, of course, we start with the coupon tests. In this case, we have two types of specimens, which are the flat and the bent. The flat is usually isotropic steel, normally as it comes from production. The bent is taken from regions where cold bending has been applied. For example, you can see the socket it's a Z-shaped plate. The corners are pre-bent, they are cold bent. So we have to account this in the mechanical properties of said regions. So in this case, instead of the plastic should start around this point, and where the flat should start normally as the classic steel curve works. We'll see this also after. In terms of more experimental tests, then we start with the tests on the parts. The first part was the socket. However, the socket cannot be tested, shouldn't be tested by itself. So we also had the T-plug part, as you can see. Dimensions, in this case, they're also specified. Shouldn't be that important. And we also, from this test, we noticed that for higher loads, there are some fragile problems in terms of, especially the weld on the T-plug. Once the weld in the T-plug breaks, the behavior might be asymmetrical, and the whole socket doesn't behave the same anymore. However, biggest problems happen for very high loads. So we hope that this is not a huge problem. So we tested also the different boundary conditions, different load directions, stiffener, non-stiffener, different widths. So we have a decent range of dimensions to further study. Well, obviously, the thickness and the width are the most important parameters, because those are the ones that increase substantively the stiffness of the whole chain of parts. Of course, also some global imperfections are also always noticed. The same has been done for the fork. In this case, I call the fork part of the T-plug. These have always stiffeners, because otherwise the part would be extremely flexible, and we do not want that. Also, this comes to terms with the idea that the socket will govern the connection, not the plug. So this should be relatively limited in terms of size and the dimensions and other features. However, we can see the huge difference in terms of the thickness of the specimen, and also the presence of stiffeners. Where there are no stiffeners, the resistance is very low. Then we have experimental tests on the joints, on the whole joint. Here we have 5 configurations where we change the presence or not of stiffeners, the width, and essentially also the thickness from 6 millimeters thickness, 8 and 10, and you can see some instrumentalization as well that has been put in the specimen. Also, this section, which represents the light steel framing of the truss with the reinforcements which were needed in this part of the truss, also in the diagonals, because the loads were too high, the eccentricity here introduced like a lot more different loads that we were expecting. So there was kind of a shift between these two parts, which made the tests and further studies kind of more difficult, but everything went through. Again, we can see that the parabolic behavior of the joint, this parabolic behavior is also very influenced by the stiffness of the truss itself. So these are calibrated through numerical modeling. So we can actually have the the behavior of the joint isolated. So the main problems were, as I said here, in the node region where the eccentricities were too high, and the bolts and screws failed in shear, or the bars failed in bearing. So we also see that usually we should expect a symmetrical behavior of the joint despite the loading direction. So this is the numerical model calibrated for the socket parts. We have some simplifications. The mesh options are also very simple, very straightforward after the calibration. So, and in terms of parametric studies using the models of last slide, we also took more conclusions. Well, they were pretty much the same conclusions as in the thickness and the width highly influence the joint's behavior in terms of actual stiffness. It is pretty much the same for the T-plug. The parametric studies were also performed, where you can change the thickness of the plate, the width, in this case the interior width, and the height of the joint. So we can see also some curves. You can also see this effect here due to the corner regions, since they have the plastic limit higher than the normal steel. You can see a slight dent here from that. Some other conclusions. Height also has influence, but is pretty much linear, so not one of the most important parameters. Also, for the model calibration now for the whole joint, this is an example of a curve that we got. We try to replicate more or less the shift that would happen in the truss in real life. This took some time, especially because we tried different simplifications for the truss due to simulation time and mesh types and everything else, gaps or preloads on the bolts, etc. So it's just kind of a complex process, but calibration was gotten. After calibration, then we start with the parametric study as well. This is better because it has way more parameters changed, namely the width of the T-plug, the height of the parts, the width of the socket, the thickness of the socket, the number of bolts, where the number of bolts is only applicable really when the height of the socket is high enough, right? And the total height of the connection. So usually we've been using a connection with 60 centimeters. We also tried with different heights, so you can see the effect of the lever arm, and how applicable is the actual spring in the global system, and etc. So we can see how here some images of what we've gotten. For example, the actual lever arm, you can see here when in bending. So this is to represent the resulting load position in the socket when acting in bending. So this is the element distribution. So the resultant should be around the height of the bolt, more or less. Actually, in between bolts, a little higher in this case. And we can also notice that for a shorter connection, the eccentricity or the resultant is way more in the middle of the socket, in this case the top, which is in tension, than in compression. So this looks like it's not totally symmetric because the resultants are in different heights, but still in the overall state of things, they're pretty much symmetric. Also, this tendency changes with the height of the connection, weirdly enough. So the bottom resultant grows further away from the edge to the middle, and this in the top it happens the opposite as soon as the total height changes. So the lever arm can be around 90% of the total height. Also this is another part of the parametric study where it was extended, in this case particularly to account for different T-plug sizes, so there was more occupied inside the socket, and also to test stiffness, as so far unstiffened have always been tested instead. Oh, also you can see in this graph that, or in this table rather, there's a factor that I considered that is TS over MS. MS is the lever arm of the socket, and TS is of course the thickness. So the higher the TS, the more compact the socket is, as you can imagine. So I use this factor to compare directly instead of using dimensions, otherwise it will be too complicated, too confusing. And this is an image that represents the lever arm, or the effective arm, of the T-stub, or in this case the T-plug, because the more stiffer, or the stiffer, I mean, the socket is, the lower the arm of the T-plug. Whereas if the socket is too flexible, the T-plug uses more of its arm. I don't know if you can actually imagine this. I think I have an image later. So, after all these parametric studies and numerical results, we part for the analytical model, whereas we had already CTICM, our colleagues, also had a proposal in terms of the thickness. However, I thought that this is too simple, otherwise there are missing some parameters, especially, for example, these dimensions, like in the direction of the load, which are not considered here, only the thickness, the MS, which is the lever arm of the socket, and the factor, which a simple factor is also too simplistic. So I decided to make some very simple analytical models based on the elastic beam theory for isostatic and for hyperstatic. This is to more or less represent the presence of a bolt. So we have a more complex equation. Also, if we have a socket like this, bending will be certainly the conditioning deformation. However, if the socket is too thick and too narrow, an axial component will take over the deformation of the socket. So therefore, it should be considered as well. So in this case, we tested the presence of stiffeners, the presence of T-plug. As you can see, a short T-plug has a different contact point. So this will condition the stiffness of the socket, and also the load direction, because you've seen it's not totally symmetric in terms of compression and tension. Actually, compression is slightly more stiff, because you can see also in this image, once in tension the socket kind of wants to open, and this happens more or less freely, whereas in the opposite direction the socket cannot close, so therefore a slightly higher stiffness is present in compression. Also, it's very important, the shape of the socket itself is very important, because it depends on if you use solid numerical models or beam numerical models, or shell, or all those things should alter significantly the stiffness of the socket, especially for lower stiffness, because the sensibility is too high. So we also made a small study in regards to the software to use. So what I decided was to, given the analytical formulas, which were not really giving the accurate results to the numerical ones, we decided that we should add some factors depending on the socket shape, the load direction, the stiffness, if there are or not, there are not stiffeners, and the plug size. So we have a kind of a guide depending on the type of socket, stiffened or unstiffened, if it's in compression, tension, etc. So you have a set of factors to correct it. So in this case, this is one of the tables of this development. So here we have the factors. I don't have here the values of numerical and analytical. However, I have the errors between those. The highest one right now is 11.7%, which is okay. So again, it depends on load direction, T-plug, stiffness, and the shape itself, because the shape itself is, I cannot have a good relationship between the analytical and numerical just looking at the shape itself, because the corners, I believe, will give total different behavior when in relation to the other parameters of the socket. So, so far the conclusions have been the connection has a wide range of rotational stiffness, because they can be really weak or really strong depending on their stiffness, or thickness is very low, etc. It should be replicable by the component method, because the actual stiffness, actual spring works very well when applied in a binary way, binary of loads. Again, I focused on the socket because the socket itself will govern the solution, the system, not the plug. Otherwise, the plug, as I said, should be stiffened relatively stiff enough so the socket can govern the connection alone. And after the corrections, after the last slide that you saw, the analytical model with some correction factors accurately represent the numerical results gotten. So in terms of further work, so we will finish on the socket, we'll characterize the plug and the fork next, although as I said variations will be limited, develop again new analytical models for isolated and global behavior, and of course global behavior as I've just said. So these are some of the papers that are already done, and I believe that is all for today. I don't know if I'm within time or not. Oh Jesus, I'm sorry.
Okay, thank you. Okay, and now, Manuela, is your turn.
Okay. Thank you, Luis, for the presentation. I also work with some kind of like modular systems, so I'm a fan.
Maybe it's better if you go closer to the mic, because I don't know.
Wait.
This is my
Thank you. Perfect. So as I was saying, I also work with modular construction, so I am a fan of this type of ideas, and I think it's something, like very innovative right now, and that we are all looking forward to. So my first question is maybe something very simple, but how adaptable do you think that this system is to, for example, like other types of columns? Here you have a tubular rectangular section, but if I give you like a standard HEA or a dolly shape or whatever,
it will be more difficult, because in that case you'll have either too many load, concentrated loads in the flanges, looking at the configuration of the socket on the side. So you'll catch the flanges or the web. So neither of those is really optimal, I would say. So I mean, unless there are some alterations, I don't believe it should be that applicable. But then again, it depends on specific studies on that, or if you have some stiffness in set columns, maybe it will work. So yeah, but we haven't tried that. The idea was to use hollow sections.
Hollow sections.
Yeah, from the beginning. But nice question, though.
And also thinking a little bit about, like the actual use of this. In terms of construction, like in the lab, for example, did you have a lot of trouble? Because it looks like the space that you have to actually put, everything in the socket, it's very, very tight. So, do you think that this would be something, that will slow down construction, or the whole system, even though this part might be a little bit difficult, could like overcome that difficulty?
Question as well. I guess you touched on a sensitive, let's say, subject, because I've presented some studies on the plug and the influence the plug has in stiffness of the socket. However, considering that, the gaps that we should have for construction, maybe the T-plug will have less of an influence because it will not even touch the socket because of set gaps, because of those tolerances. So yeah, we should have a slight margin for tolerances, as I've heard, like guys in the lab had some trouble, had to use some hammering,
Yeah, because you said at some point you talked about the gaps, so I was thinking maybe
strict dimensions. Yes, you're right. So yeah, you should have. Also, I forgot the question though. What is the question?
No, just if you think that the use of that part of the process, of the construction process, might be like slow, but do you think that the overall use...
as long as these are accounted for. Also, you can assemble it in the workshop to test it before, even if it's just some parts or some frames, just to make sure that everything works out correctly. But yes, some tolerances must be given since all the gaps in the single lap joints, etc., etc. So yeah, those are very important and very good point.
And then maybe, because you said that the connection is moment resisting, right?
Should be.
So was there any kind of investigation about, let's say, buckling in the column, or how does the column interact with the... Because
not really.
like, I don't really know about the topic as much as you, but if you look at it, you can see how probably, there's like a concentration of stresses exactly where the welds of the sockets are. Like, that's how you are going to transmit the force from the socket to the column. So I don't know if you think this might affect the column in some way.
It could affect the column if the loads are high, and especially if the socket is too narrow, because then the loads will concentrate in the web of the column. I mean, not in the web, in the flange, but in the middle part of the flange, of the column. So then you could have some problems in terms of stability. However, as I said in the beginning, I focused on the part, and the column is not yet really studied in that regard. However, as long as the socket is wide enough, and it should be okay.
And well, I think something that's that weld is very interesting to me.
The weld between the socket and the
column. Or in your opinion, in slide 6, you presented like all the components.
isto, não é?
So, for example, what is the difference between 2 and 3? Because from there I couldn't see, but now it's a little bit.
It's the welds and the column itself, if I'm not mistaken.
Okay. So yeah, for example, in the socket you
should be the weld.
have different things. You have, let's say, like number 3 that is the weld. Then you have 4 that is like that web. Do you have you identified one of them that is actually in the socket the most critical one?
The weld shouldn't be a problem. The weld, even if for high loads, was not a big problem. This weld here in the T-plug, yes, could be a problem for higher loads, and if the socket deforms enough, yes. But those, not really, not that we have seen so far, to be honest. But the most important one should be the socket in bending. So the stretching or compacting of the socket itself is the most governable part, and we are focusing on that.
And then, for example, if we would be talking about some kind of a seismic design,
yes.
So the socket is the most critical. And
surely, it will probably present too high deformation for cyclic. I'm not really sure. Maybe we should consider for cyclic, since very, very specific and very difficult to assess load, right? Maybe we should think about applying OSB panels, maybe.
yeah.
Because I'm not sure even in cyclic behavior how they work still. So it's very, very green in that regard in terms of cyclic behavior.
And maybe this part is something that I didn't really get, but you talked about when you did the parametric analysis, I think, that you were expecting symmetrical behavior.
Yes.
But it didn't really.
Not really.
What do you think that maybe it was not exactly symmetrical? Like, do you have some clues about?
As I said, like one of the last things I said, I don't know, I can present you the graph even. So you can see here, compression is slightly depends on the part of the. So for more compact sockets, compression, you can see the difference in compression is slightly higher than tension. When no T-plug is applied, like this is just a plug, just a socket. So as I said, I think this is the case. So when it stretches, this part opens, it goes off the T-plug. So it's okay, it can go. In terms of compression, it wants to go inside and it cannot. So I believe this is the main reason. There's that slight
So it's like a self-rigidity, like a self-stiffness feature that maybe the whole assembly gives.
Yeah. So when you have tension and compression, there will be always a slight difference, but in the great scale of things, hopefully. And if the connection has this decent height to work with, so also what I've noticed and I presented is that for lower height, so this is, for example, 60 centimeters, but if you have 40 centimeters in tension, there will be more in the center, and in the compression it will be lower. Well, if it's 1 meter height, it's pretty much the opposite. So this is some kind of complex behavior. So there's many parameters. So after I've seen what influence there is on a global scale, well, might as well understand what happens in the isolated in the smaller scale.
Then I wanted to ask you about those factors. Like, so as I understood, you define those factors to match your numerical analysis to your analytical analysis.
Exactly.
That's
yes, and in just for curiosity, I use both mine and the CTICM. The errors are pretty much similar as well. Well, of course, each factor, this factor here, the shape. I don't know if you understood what I wanted to say, but given the ardent corners, if a socket is wide or not, I cannot really replicate that just a simple beam with a different size. When we can see the solid, there will be extra effects on the corner, and the behavior will not be as predictable. So I call that the shape factor. So yeah, well, applying then, if we have like some type of socket, we just decide which alphas, and directly we should get the. So, but this is just the beginning. In other words, there are many parameters. Also, the total height, as we just talked about. So, it's a complex and long process. But I think I got more or less accurate results after the whole thing.
Maybe the final question. It's about the conclusions. So you said that the connection has a wide range of rotational stiffness, but do you see this as a, let's say, positive feature or something that you would need to control if this is released to the public,
Both.
let's say?
Both. There's a wide range, so you can have whatever you want. But yeah, you should specify limitations or at least warn about some specific cases, or if the socket is too flexible, or the opposite, or if the socket is too rigid, I don't know. So yeah, I think that's an advantage, having a wide range, right?
Yeah.
So it depends on the designer, and what he wants to, what kind of stiffness he wants to in the structure. Hopefully, it will work for them.
Thank you, Luis.
Thank you.
Yeah, it was very interesting and for sure very similar to what I do, but from a completely different point of
Hopefully
view.
It's not
and,
too confusing, too much information.
Yeah, thank you so much.
Thank you, Mariela. Thank you, Luis. And now, other questions? Yeah.
Thank you for your presentation. Since you have done like a large set of experiment on testing, I'm curious to know during the fabrication or assembling the test setup or this specimen, what was the most difficult challenge that you faced, and how did you overcome that? And the second question, then you will reply.
Well, the only experience that I've had was put the specimens in the setup, because they came pre-assembled. That was the problem, especially all of them. I mean, the parts came pre-assembled, and the cantilevers, the specimens also came pre-assembled. It was different in the building, but I was not present at the time. I've heard some stories, because it was rather difficult in some cases because of the low tolerance, but other than that, I believe it was okay. But anything specific?
Yeah, and then later you said that the variation of the test with the thickness of the blade or some other aspects. I'm curious if you can do a preliminary design first, because these tests are really expensive. So, like, in my point of view, variation of the thickness maybe is not a very, let's say, optimal idea to do the test. Maybe like few tests, and then with parametric study you can reach to that.
No, that was the idea. Like, we tested 5 configurations, then we calibrated. Then we used somewhat different ones. So we used, in the tests we had from 6, 8, and 10 millimeters. I mean, the most variations in the parametric study were more in the width part than in the thickness part. However, what would you be like the main parameter that you should change? Because I believe that thickness should be one of the most interesting and most important parameters in the connection.
Because we did not the same test, but with similar configuration. We did only one test. I mean, 3 repetitions, 1 test, and then with calibration of that we're going to.
Well,
because thickness, if you have a reliable numerical model, then changing thickness will give you a good conclusion later.
Yeah, but you should be certain about that difference in experimental testing. So I'm not sure if they are completely avoidable, or at least it gives you a better sense of a better confidence vote, rather than say that.
So you can give us like a suggestion for our future work in the test to like avoid the like extra jobs.
Well, if I had to, not really in, in the way that you're asking, but if there was a problem in our test, would be like in the joint test, we shouldn't have put the truss as we put because it conditioned a lot of the results and it kind of made it more difficult for the calibration to the comprehension of the behavior, etc., etc. So if try to make it as simple as possible with less variables, so you're right. But I believe still that the thickness was one of the most important parameters there. So if I had to take one of those, either the boundary condition on one side or the other, I mean the column was okay, it was stiff enough, but the truss conditioned a lot of the post work.
One question?
If we have time.
Thank you, Luis. It was interesting. Think about and I want to know for myself. Do you think what is the behavior of the connection? It is rigid connection, do you think? Or imagine I'm a designer, I want to design this.
Depends on your socket.
Depends on?
On the socket, mainly. Because if you have a 6 mm socket very wide, it's certainly a pin joint, almost. If it's stiffened, very thick, narrow, it can be like almost full strength. So you have therefore the wide range of.
So now, if I want to, for example, design this connection, I don't have any.
No, not yet, not yet. But that's the idea. It's the idea to develop the whole design process of this. So yeah.
Because as a designer, for example, because I maybe want to design and I don't know, is it flexible or I don't talk about numerical models and computation. Imagine I'm a designer in GitHub, so I want to design what's that. Okay, it should be fixed or something like key connection.
Yeah.
So I think it depends on the future result first.
That's the global behavior. So far I've been more focused about the isolated behavior of set parts. Then I've been verifying in the global scale of things, but there's a way to do this in stages. So once we have the good component chain, we have the global behavior, and then we'll see how the characterization of the joint is, like you said.
And about the construction thing, when you do the welding of the connection to the column, you do welding for first. I don't know, it is feasible to weld inside or not. Definitely, probably no. But you should weld outside of that plate that connected to the column. And when you do a welding, I guess your column that you used was SHS column, box column. And when you do that, the behavior of that plate will be completely changed. It will be brittle
of the column?
Because of the connection. The part that you welded to the column, something like a switch, welded to the column, yes? It was welded. Can I see the pictures?
If I have a close up.
The second, next one. This part that is connected to the column, the vertical phalanges are welded, yes?
You mean this part in white?
Yes.
Yes, they are.
They are welded. And do you think the behavior of that connection will not change because, when the welding done on those parts of it is a thin plate, and when you welding, behavior of material of steel will be something like brittle.
Yes,
Do
yes.
you think it has effects? Because I think you expected the plastic joint or plastic deformation will happen on the socket. Yes.
On the corners of the socket. If those happen, because sometimes the deformation of the plate itself is enough to give enough rotation for the whole joint. So to focus on your question, I mean, it of course it alters slightly the behavior of the socket, but since it's in the root of the socket, and since the loads that will be applied shouldn't be enough for fragile failure in terms of the web, at least so far that I know of, no failure in the web has happened, and we tested for above 400 kilonewtons, so it's a lot.
So when you did the test, you have a column connection or just you test on the connection? You know, I'm talking about the welding part.
I'm not sure if I understand the question.
The test that you did in tensile test was
So the other ones?
test on the connection.
So you're talking about?
Yeah, it's this one. You used you did experimental test, yes, and you used the column and just the sockets and the connection part.
So in this case, these were the first tests ever performed. That we included that we called it the boundary condition difference. So we tested with rigid plate, what we called a rigid plate, so there was no deformation, and we tested also some configurations of column. However, we decided that circular in terms of the welding would be too complicated because we have to catch the side of the column, and the socket will be too stretched out as well. But yeah, this was one of the boundary conditions that we considered in the beginning. Yeah, although quite limited because the height of the specimen is probably not enough to understand the column behaving, but still one of the concerns that we had in the beginning. Yes. But then again, welds were, at least in that region, were not a problem. We can consider it almost infinite rigidity. Yes.
Thank you.
If I may, building on the last question that we had, you mentioned that you have to use different material models for the corner regions and the flat regions on the socket. I'm just interested in knowing how much the variation was between regions and what parameters you changed between the hub, corner elements.
The curves. So we have curves for flat, for bend. This is only a difference when applying the mechanical properties in ABAX, for example. Right? So we have a normal curve for the normal steel, let's say, but for the corner regions, we use the curves as well, but for a strain of around 0.3%, if I'm not mistaken. So yeah, it would only plasticize once that strain was gotten. So most of the cases the socket was plastifying except the corner regions. They were still in elastic range. I'm not sure if that answers the question though. I may not have explained this too well. But understand, like the properties of the corner are slightly different because they have been bent already.
Yeah. It was just asking you to have it at the top of your head, saying, okay, it changed by this much percent.
I don't, sorry.
That's your results and answers.
Not sure.
Congratulations, Luis. I just have a small question. When you presented the components, can you go to that slide at the beginning?
This.
That transversal element that you neglected. Why it's there, and does it affect the behavior?
This will, yeah, well, in theory it does, as I explained and showed. However, in practice, I'm not sure it will because of the tolerances that we will have to have. So, at this point is marked as neglected, but not really. It should be accounted for just, well, until we are sure in terms of practical applicability, I think. But yeah, in one way or another, I think if I have to consider, I would have to include it in the socket part. So it's also a part of the socket in a way. But we are still not sure. Because you can see here, this gap, I'm sure this is not at scale, but there's a gap already, and if the rotation is not high enough, it will never ever touch the socket. And also, if it has to touch, it is only in tension. In compression, it doesn't. So it just goes towards the column. So it's an iffy situation at this point. However, we already have an idea of how much it can influence in tension and the connection.
Very quick question. In the component curve, the joint curve, you have like two parts. Sorry. Yeah, that was not before. Yeah. So you have always this kink in the curve. So what is the change that is produced in the joint? What was the physical reason of this?
Literally the tip plug. So you can see the load upwards. This is in tension. This is in compression. You can see not from here, but there's a slight rotation in each part. And the T-plug on the top, the edge of the T-plug will touch the surface of the column. So there's a new point of rotation. So where does it start here, more or less in the center? The point of rotation becomes here because it touched the socket and then it's basically only in tension. But at that point, the rotation is already too high for practical purposes, I would believe.
Okay, but the stiffness is increased. Like suddenly.
Of course, because the lever arm is it's double almost.
The question is, why don't you fill this gap from the beginning, and then you will have like a higher stiffness?
It has to have a, how do I say, a range of rotation, right? It should be shorter, maybe. That's why I wanted to consider that length of the socket as well, while the CT ICM simplified didn't have one, that consideration. So yeah, I tried to solve that. So now, if I want to shorten it, maybe my equation will help me in terms of making this more usable in practice. So the idea was to shorten this gap so we can have this behavior before.
I don't know, it could be a possibility. This seems that there's desirable from this moment. So if you want to stiffen the connection, I mean, because it might be too flexible for some purposes.
Yeah, but it should be very predictable when the change happens. Otherwise, it will be like very.
And the other commentary I wanted to do is that I think that the asymmetry in the behavior of the component of this plate is because of the contact. You can show the images.
Which ones?
The socket.
The socket. I mean.
Yeah. So I think in the left part you can see that what is moving is the contact point of the socket with the central plate. When you have compression and tension, this contact point is very different, and I think the reason of the asymmetry is that.
Yeah, it's pretty much it. And if there is a T-plug that actually contacts this next string.
And my last comment is that for cyclic behavior, I don't think this is a good choice of connection, because the problem is that you don't have lateral stability. The connection is very flexible on the lateral and the weak direction of the. So if you have like a cyclic behavior, the bottom part of the truss will be in compression, and there will be a high instability.
Well, in cyclic Well, if you look at the frame, one is the tension, the other is compression. So
Yeah, sure. Yeah, but close to the connection, the bottom part will be in compression, and because of the type of weak inertia in the weak axis, I think you would probably have a like instability.
if you have a socket like this, for example, it's not as flexible. This socket is very stiff.
Yeah, but in this cross section, there is like a point with no flexibility, with all the flexibility. The central part has no inertia. So if you apply a bending moment like this, then the whole thing will rotate very quickly.
Oh, in the other direction. Well, we count for the slab to do something.
Yeah, but you don't have the slab, you have inversion of moment. That's what I mean.
Or we can add extra parts for the truss. It's already light steel frame, so a couple of maybe. Is that all?
Okay, thank you very much.
Thank you.
Thank you very much, Mariela, and thank you very much for your question. Next week, we'll be here at the same time.